Hey class, let's talk briefly about temperature, and let's focus on the physical nature of what temperature is actually measuring, the common scales used to quantify temperature, and then let's apply these concepts to the basic operating principles of a simple alcohol-based thermometer. Now, it's easy to focus on hot versus cold when it comes to temperature, but what we have to realize is that fundamentally, temperature is actually measuring the mean kinetic energy of the molecules that make up a substance. So when it comes to air, we're actually measuring how fast the air molecules are traveling. We can visualize this with a simple animation. So here we have a jar of air, and we see all these air molecules in there, and they're moving really fast because we're starting at 90 degrees. But as we start to pull energy out of that jar, notice how the air molecules are slowing down, and then our thermometer is measuring a lower and lower temperature down to 50 degrees. But then as we start to add energy back in, the air molecules get faster and faster and faster, and we thus measure a higher temperature with our thermometer. Now physically, the sensation of warmth versus coldness is created by how often the air molecules are striking our skin. Because as the air warms, more molecules are striking our skin with greater frequency. That energy transfer is thus giving us heat, and we feel that warming sensation. Now what we also have to realize is that as air is heated up, the air molecules have more energy, they're moving faster, they're exerting more force against their surrounding environment. So air will actually expand as it warms up. And we'll use this when we think about measuring temperature. Now, just like we can express length in meters or miles or inches, we have three different scales to quantify temperature. And those are the Fahrenheit, Celsius, and Kelvin scales. The Fahrenheit scale is based on common temperatures that we experience in this part of the world in the outdoors. So 0 to 100 are kind of our extremes. Then by definition, water at sea level will boil at 212 degrees Fahrenheit, and then ice will melt around 32 degrees Fahrenheit. Whereas the Celsius scale is fundamentally based on the boiling and melting points of water. So then water boils by definition at 100 degrees Celsius, and then ice will melt at 0 degrees Celsius. The Kelvin scale is often used by scientists because it's fundamentally based on the physical principle of temperature, the molecular motion, because as temperature increases, we know molecular motion is getting faster. So we define 0 Kelvin, or absolute zero, as having no molecular motion, and then temperature will increase as the molecular motion gets faster. And it turns out that water then boils at 373 Kelvin, and then ice will melt at 273. And then we can use some pretty simple equations to convert between scales. Now I think we all know that thermometers are the instruments used to measure temperature. Well, it turns out the first thermometers used the basic principle of volume expansion in order to get at that temperature measurement. A simple example of this is the alcohol thermometer, or liquid in glass, which is a form of conventional thermometry because it utilizes this principle of thermal expansion. So we have this glass tube with some alcohol in it, and then the remainder of the open tube is a vacuum, and that is where the alcohol can expand. So as the air temperature increases and warms the alcohol, we have thermal expansion, and the alcohol moves forward down in the tube, thus measuring an increase in temperature. So we warm up the alcohol, and then we see that thermal expansion giving us that higher temperature reading. Electronic thermometers work a little differently. They use thermistors, which are a little piece of metal, usually nickel, wrapped in a protective coating. And the resistance that's measured across the metal will actually change as a function of temperature. So as the temperature changes, we can measure that resistance difference and then convert that signal to a digital readout. We're almost done, but let's think about one quick interesting application of the physical construct of temperature versus our feeling of hot and cold. Remember the thermosphere, that uppermost layer above 50 miles? Well, notice that temperature increases with height in the thermosphere, and in fact, the temperature gets so hot, it's even warmer than down where we live in the troposphere. Well, this is where satellites fly, so how can this actually be? There's barely any air molecules up there. Well, that's the difference. The air molecules are actually really excited by solar radiation, and they're moving really fast, so they give us a high temperature if you actually had a thermometer up there. But if you were out there, there would be barely any air molecules to strike your skin to transfer that energy, so you would feel extremely cold. But there's still a cool application here. Even though they're few in number, the remaining air molecules at this altitude can actually interact with high energy electrons that originate from the sun. And when they collide along Earth's magnetic field, they'll actually release a brilliant light, which you probably know as the Northern Lights or Aurora Borealis. Now come on, that's just cool. Alright, that's all for now. Till next time.